So on this first question, we have two claims. We want to check if they're true or false, giving an explanation if it's true or a counterexample if it is false. So here is the idea here. On this first equation, this first claim, it's pretty simple. We don't even need a counterexample. An explanation will suffice. Starting with this, you have a of x equal to the integral from a to x of f of t dt. And we're told that big F is an antiderivative of little f. So that means by the fundamental theorem of calculus that this is the antiderivative on x, that's the top limit of integration, minus the antiderivative on a, that's the bottom limit of integration. So that means a of x equal to this. Therefore, a prime of x, you can derive both sides. That's the derivative of the left-hand side, which equals the derivative of the right-hand side, which is f prime of x. And the derivative of this equals to 0 because that is a constant, right? Just f of a, it's a number. So a prime of x equals to f prime of x and not f of x necessarily. So as long as your f is not, as long as you choose a clever x that is not equal to its own derivative, then this is a false statement, right? This is not equal to, a prime is not equal to f of x, it equals f prime of x. It's pretty important. You could also, if you wanted to, just pick some numbers. If you wanted, you could just pick like f of t equals to t or something, right? And maybe a equals 0. And I think that would, if you do the math, you'll see that an antiderivative is t squared over 2. And you'll see that a of x is actually, the same as f, rather than its derivative. So we're going to see that it is not equal to, the derivative of a is not equal to f, to big F. All right, so that shows it's false. And now on B, this is a little more convoluted reasoning. The idea here is that you have a continuous function that's being integrated, but not the function itself is being integrated, but the absolute value of the function is being integrated. So this means that if you have some function that looks like this, you're actually reflecting everything that's below the x-axis up, back up, and then you're integrating. So we're actually calculating this area under the purple graph instead of the blue graph. So the consequence, the number one consequence of that is that whatever area we get, if we do get any area, needs to be non-negative, meaning 0 or positive. It can't be more than that. Or, it can't be negative. So, what we say is that if the integral equals to 0, then the function itself needs to be 0. And the reasoning, once you understand what's going on, is because if f of, say, some point were different than 0, then the absolute value of that thing is positive for sure. Not greater than or equal to 0, but positive. So in your drawing, right, your x0 is definitely above, and therefore there's some positive area here, some non-zero area. And if that happened, you would have the integral to be bigger than that green area, which is positive for sure, right? So it cannot be 0. If you have one single point such that f of that point is not 0, right, then the whole integral has to be non-zero, has to be strictly positive. So the reverse needs to be true. If the integral is 0, that means all points need to be f of x equal to 0, need to be zeros of your function. Your function needs to be to have 0 area. Your function is this horizontal line on the x-axis. Okay, the graph is. So this is a true statement.